Hi, thank you for joining us from around the world. Welcome to the Global AI Community on Tour, and we are getting ready to speak with Tess Ferrandez-Norlander. If you have
Hello.
any questions during the session, please feel free to post them in chat.globalaicommunity. Tess is a developer, data scientist working at Microsoft. She has over 20 years experience. She has changed the way we do .NET debugging, developed a large number of mobile apps, and as of a couple of years ago, she moved into the world of data science and machine learning with a lot of the largest companies in Europe and beyond on really tough ML programs. So welcome, Tess. We're excited to have you today.
Thank
And we
you.
also have Amy, who's back with us this morning. So welcome, Amy.
Hi, everyone. Nice to see you again.
Hello. So should I get started?
Yes.
Okay, cool.
Thank you.
I'm Tess. I'm a software engineer and data scientist at Microsoft. And on a day-to-day basis, I normally develop machine learning applications. But what I'm going to talk about today is not necessarily how to create machine learning applications, but rather how to not create machine learning applications, or how to not get them wrong, at least. So around a couple of years back, a couple of researchers from California created a machine learning model to accurately determine if a crime was gang-related or not. They did this for the police, and obviously that would be a really good thing, except for if it goes wrong. So in the cases where you maybe think that something is gang related, but it's not. In that case, both the perpetrators and the victims would be treated as gang members and probably added to the CalGang database, the California Gang-Related Activity Database, which is also a database that this research was based on. Now, this being in this CalGang database has a number of different problems. First off, it has some problems with how long people are retained in the database. So essentially, once you get into this database, you never leave. And then it has some privacy problems, like people outside can actually go in and look and see who's in there to determine if they should hire them or not. So being added to this database is quite bad. And this database also went through an audit where they found that about 25% of the data, or the people in there, actually didn't have any proven gang-related affiliation. In fact, 42 of them were under the age of 1, out of which a full 28 had admitted to being active gang members. So you can see how this data was not really very appropriate for machine learning, because in machine learning it's always crap in, crap out. So when they presented this at a conference, some people had questions. They questioned, what did you do to mitigate the problems with the data that you were using? How did you make sure that your models were not just predicting gang-related because someone had a certain ethnicity or lived in a certain zip code or something like that? And the presenter said, I'm just an engineer. To which a lot of people were getting very grumpy, not least Blake Lemoine, who stood up, walked out, and quoted a song by Tom Lehrer saying, so once the rockets are up, who cares where they come down? A song about a World War II rocket scientist, Wernher von Braun, whose rockets were supposed to land on the moon, but unfortunately landed in London. But he was just an engineer, so was it his responsibility how these rockets were used? I'm suggesting that maybe we're not just engineers. Maybe we have a little bit more responsibility, because we're put in charge of creating systems that decide if someone should get a loan or insurance or things like that, or if they could be put in jail. Or now, for example, with the ongoing pandemic, modeling decides what actions we should take to see if to make sure that people live or die. So we're being put in charge of some very, very consequential systems. You might be familiar with this, I'm sure most of us are, the Cambridge Analytica scandal from a number of years back. This was loosely based on some research by this guy, Michel Kosinski. Now, they're not related, but the research is very similar. So he created some research that you might also be aware of, which was basically, given 50 likes on Facebook, I can tell you who you are better than your friends and family. I know I filled out a couple of like these, hey, given my Facebook feed, tell me what my political affiliation is or whatever. And it turns out it's very possible. But he did this primarily to illustrate that this can be done and that this shouldn't be done. He later went on to create another very controversial paper called the AI Gaydar paper, or it wasn't really called that, it was called something completely different, but commonly it's known as the AI Gaydar paper. And this paper is very much what it sounds like. Given a number of pictures of people, it could tell whether or not what someone's sexual orientation was. Now, again, he did this to prove that it could be done, or to illustrate it could be done, to sort of illustrate that their privacy is a bit at risk if we're letting these things happen. So what we're seeing here, actually, this paper had some method problems, and he admitted that this paper has some method problems, but what we're seeing here is combinations of images. So, for example, men who like women. This is a composition of many, many pictures of men who have this sexual orientation. Now, some of the method problems in this data was that all these pictures were taken from dating websites, maybe locations where you might show your affiliation a little bit more. And it had some other method problems, like, for example, the way they were calculating accuracy and things like that. But the question, whether or not you think that it's doable or not, is should we actually be doing this? And what does it actually mean? Because classifying a trait like your sexual orientation on a scale from 1 to 0 has some very weird effects. First off, what is a 1 or a 0? Is a 1 standing in front of the Pride Parade and a 0 homophobic, or where do things fall in between? What if you're bi-curious or bisexual or transsexual or whatever? See, there's like a long scale, and there's not really a 1 or a 0, so these can't really be classified as shares or cats or dogs or things like that. So first, there's the obvious problem of that we can't classify them. The second problem is if we do classify them and if we get it wrong, we have some very bad consequences. Now, in Sweden, it's not a big deal how I'm classified, or if I'm classified something differently than what I think, because I probably wouldn't lose my job or anything like that. But in other countries, this might be something that's criminal, sometimes punishable even by death. So it has some very, very important consequences. And on the question of can it be done, this model that was created was merely a stereotype looking model. So it found, for example, that women who like women have this shadow over their head, which equated to wearing more baseball caps, for example, and wearing less makeup. And the men who like women are worse at taking selfies because their nostrils are visible and things like that. So, things like that. But either way, we shouldn't be doing this. And on the criminal aspect, there was another team of researchers that did something very similar. They created a model that basically took images of people, random people, and could tell if they were criminals or not. That would be very useful, very person of interest style. So what they did was they took around 2,000 images of men, I think 18 to 55. Some were criminals, some were non-criminals. And you might think that to be able to accurately describe if someone was a criminal or not, it would have to be sort of like super violent criminals, like Hannibal Lecter style. But no, it turns out that most of these people were not that style. It was any type of criminals. But what they did have in this case, and this kind of becomes important, is that the criminals were government-issued ID and the non-criminals were corporate headshots. So once, and what they found was that in the criminal phases versus non-criminal phases, they found this very, very, I don't know what you call it, like theoretical or scientific information that this area told you if you were a criminal or not. I would like to show you two pictures. A government-issued ID, or at least Microsoft-issued ID, and the corporate headshots. I think it's fairly easy to determine which one is which out of these. But independently, if we go back again to the classification of 1 or a 0, what does it mean to be a 1 or a 0 here? What does it mean, for example, if you're if you had a speeding ticket, or should you then be classified as a criminal? And when like having a model like this sort of assumes either one of or two things: either A, that you become a criminal and your face changes as soon as you're committing a crime, or B, that your facial structure is the same and that you're predetermined to become a criminal from the get-go. And this is a weird thing to me, at least. Now, the other thing that's quite interesting is that they had 90% accuracy, and this was at a time when AlexNet was the big architecture, or the best architecture for computer vision. An architecture that could accurately determine if you were a man or a woman in 86% of the cases. So criminal 90, gender 86. I think not. But the question is maybe not can we do it, but should we do it? Kate Crawford, she used to work at Microsoft, but she's now a researcher at the AI Now Institute for FAIR AI. She said, "We're currently in the biggest experiment of classification in human history." And the problem is that we're not only in the biggest experiment of classification in human history. We've done this before many, many times from Aristotle and throughout the years. But the problem is that now we're doing it at scale and without people knowing about it. And that is quite scary. It's quite scary that we have companies like these that can exist, that can classify someone as terrorist or not, and that these are actually being used by governments. Now, because one of the problems is that once, like, even if we think that, okay, it makes no sense that something should be able to classify criminal or not in 90% of the cases and gender in 86% of the cases. But as soon as we put it through an algorithm, we end up with a situation where we trust it because it's a machine. So one of my friends, Bill, he went to the hardware store because he was remodeling his house and he was getting some 2x4s. He got to the cashier and the cashier scanned his 2x4 and then it didn't work for some reason. So the cashier called someone else over, they scanned it again. And then looking at Bill, looking at a 2x4, looking at the computer, they said, "We don't carry those. We don't carry those because the computer says no." And this is exactly what we're doing with algorithms that sort of spit out answers and suddenly validate them. A quick sort of a responsibility laundering. Another thing we hear a lot is algorithms can't be racist because they're just math. And yes, math doesn't have feelings, it doesn't have preconceived notions, it doesn't have any of that. But the problem is that the algorithms that we're creating are not just math. They're very much the data that's behind them. So I am not a big Star Wars fan, I have to admit, which I maybe shouldn't admit in a very nerdy or computer engineering setting. But it means that, for example, I don't know one Wookiee from the next. I don't know Chewbacca from his wife, because I haven't been exposed to them a lot. Same way with machine learning. If machine learning hasn't been exposed to something a lot, they also don't know the differences. So most machine learning models in computer vision are built on or transfer learned on top of this huge data set called ImageNet. An ImageNet is a data set of search queries, mostly US and Europe search queries. It's actually largely built of dogs, because at one point they wanted to have a little bit more, like they wanted to test out some models with dog breeds. So, and there's a lot of different dog breeds in there. So if you're going to classify a dog, ImageNet is king. But it has some severe problems because the bias of US and UK, or sorry, US and Europe causes problems like this. You see this picture, you send it into any cognitive surveys or pre-trained models, and you get something like this. So whilst millions of people know that this is cricket and not baseball, this is not something that most computer vision models have been exposed to. And this also causes problems, for example, in facial recognition. So in facial recognition, we have, for a long time, we benchmarked them against something called labeled faces in the wild. So this is a data set of headshots of people who were in the news, in Yahoo News, from 2002 to 2004. Now, if you picture who's in the news and who gets headshots, it's typically very male. So 77% of the images in here are male, and 80% of them are pale. And a full 5% of these people are actually George W. Bush. So if you want to classify George W. Bush, a face recognition system will do that perfectly for you. But if you're not George W. Bush, then you might have a different problem. So when you're creating systems that use computer vision, you might end up with something like this if you don't train it on the full population of the people who are going to be using your systems. Or you might end up with something like this. So this is a picture of me about 2 years ago, maybe. Now, as you heard, I've been in the business for 20 years, so I'm obviously not 26, but I'm also not a man. And unfortunately, most of these systems think I could be a man. I think mainly because I don't wear a lot of makeup, and I have maybe some more male features, but also because it's not trained on people like me. Like, it's not benchmarked on people like me, because the women who were in the news 2004 to 2008 or 2002 to 2004 were largely actresses and these kind of people, or politicians, but I don't think I look like neither, so that's a little bit of a problem. Now, so one person who's been researching quite a bit around this is Joy Bolin-Winnie, and she came out with a paper a while back called Gender Shades. So if you look at the picture, you'll see that she's wearing a mask, a white mask. And the reason why she's doing this is because when she's using face recognition systems, she's not even visible to the face recognition systems. because they simply haven't been trained on any one hair shade. So she has to wear a mask to even be recognized. But she did some studies on face recognition systems, and specifically looking at gender evaluation, so whether or not they could determine what gender you are. So this was in 2017, 2018, and we could see that in total, most of these actually had like 100% accuracy on the full group, specifically when you looked at the benchmarking. However, for example, if you were a darker female, it guessed you wrong 1/3 of the time. So every third time, you were a man instead of a woman, because the majority of the training material and the benchmarking material were women. So even when you have the accuracy of the larger group, you might have accuracy problems in smaller subsections like this. This causes problems like this. So this was in 2018. This black man was patted down by the police on the floor and everything because he looked like someone on their wanted list. The problem was that he was not. He wasn't even related to the person. But the face recognition system had not been trained enough to determine that, like to see the difference between two black people. Now, the good news here is that this has changed quite a bit since then. So when this became apparent, then these companies started working a lot on these systems, and IBM actually came out with a very much more diverse benchmarking set that anyone can now benchmark against, that has a lot bigger variety of different ethnicities and genders and so on. So it's looking way, way better now. So for example, Microsoft has almost very similar accuracy across all of these shades. Now, some still have problems, but at least we're getting in the right direction. So saying that algorithms can't be racist because they are just math is a little bit like bias laundering, because as soon as you take it through an algorithm, you can't just assume that all your bias is gone. Your bias will still be there if the data was biased. And this doesn't only apply to images or video. It also applies to text, for example. So most text recognition is trained to semantically extract information about words. So for example, if you look at the word computer, then you have NLP systems or natural language processing systems that extract and know that, for example, it's a machine, it's something that has a keyboard, blah, 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 like something that gives the word computer a meaning, so that you understand that there's a difference between beach and peach. But for example, apricot and peach might be very similar. So that's quite useful to extract that information. However, when you extract that information, you also extract some of the biases in the data that you're looking at. So this is Google Translate, and if you put in, she's a computer programmer and he's a nurse, and then translate that into Turkish. Turkish is a language neutral, is a gender neutral language, so it doesn't have he or she in the sentence. But then you translate it back, it automatically translates it back to he's a computer programmer and she's a nurse, because computer programmer is statistically more likely to be a he. So this can, of course, this shows the bias of the words. This doesn't only apply to things like computer programmer or nurse, but it also applies to adjectives. So he's beautiful, she's aggressive, she's guilty becomes the opposite. Now maybe that doesn't feel so comfortable, and that actually causes problems like this. If you're doing word prediction, and you have the doctor hired the assistant because, and you say he, then it might predict who was too busy. So, T9 or whatever. However, if you say she, it might predict was really good at typing. So it's now referencing the wrong subjective or the wrong noun in the sentence. It also causes problems like this. If you're going to do something that looks at CVs to determine if someone is a good candidate or not, even if you remove everything that you think is relevant or could tell if someone is a female or a male, it may still pick up whether it's a female or a male by just looking at the words and just looking at the connotation and the usage of the words. So this is why they had to scrap it, because it could definitely determine if it was a man or a woman without having gender in the field. Another problem that we can also run into, that's a little bit scary, is a confirmation bias bubble. So you might have already felt this a number of times. For example, you go into Google and search about something and you get a totally different result than some of your friends, because it tends to feed you with information that's similar to what you've searched on before. Or for example, if you look at your Facebook feed and all the opinions seem like yours, and for some reason, like people with different opinions maybe are a bit hidden from you because you haven't liked them enough. So whatever you start liking or whatever you start clicking on starts becoming this confirmation bias. So you start ending up in this bubble where everything that you see is everything that you like. We see the same thing, for example, and this is an example from searches where if you search for the word CEO, obviously there is a big bias in society as far as like male or females when with CEOs, but the problem sort of becomes even bigger here, because if you search for CEO and your first 3 or 4 rows only show males and the first female only shows up very far down, then people will generally click the first 3-4 links, and now they'll be fed back and say these were the most popular ones, and now you start creating sort of a positive feedback loop that feeds into your machine learning system and eventually just removes all the minorities from the list. A similar feedback loop is if you have an area with very high crime and then you send more police because you want to take care of the crime. They do more arrests, which obviously is good, but this now feeds into to the system as it appears to have even more crime. So using arrests as a proxy for crime, we now send even more police and do more arrests, and we get a runaway feedback loop. So the number of crimes have not increased, but the number of arrests increased because of our actions that we're taking, because we're acting on this feedback. Quoting DevOps Borat, to make an error is human, but to propagate the error to all server in automatic ways is DevOps. The same for AI would be to bias is human, and to propagate bias to all server in automatic ways is AI. So how do we solve this? Well, it turns out that bias is an NP-hard problem. And by NP-hard, I mean it has so many different variables and so many different potential solutions, and no solution is a given. For example, let's say with the words, you could, for example, remove the gender from the words. You can actually clean them and neutralize them. But then you have a problem with what words you would actually neutralize. Do you neutralize something like computer programmer? Yeah, probably. And do you neutralize something like pregnant or colorblind or or things like that. And then the question becomes a little bit more shady, and it becomes very subjective. The other thing is that it's easy to say with male and female, but what do you do as far as ethnicity? You can't, what is the neutral ethnicity? Then you have to neutralize, for example, between Latinx and Black, and Latinx and Caucasian, or in all sorts of things. And it starts getting very, very, very complex. And if you neutralize everything, you remove the meaning also. So you don't create meaningful machine learning systems. Instead, you need to sort of look at every case and try to figure out what possible solutions could be. So let's take a loan system, for example. If you have a loan system and you try to figure out if someone should get a loan or not, and you see that there is a high bias that, for example, men get a lot more loans than women, then one option you might go for is remove gender and we're done. Well, that might not solve the whole problem, because there might be reasons why females don't get loans when they should. One example would be, for example, if they have a gap in their employment history because they've been home with their children, but they now have a very good job. So then we could do something like equal outcome. We could say, hey, 30% of the males should get loans and 30% of the females should get loans. But that might not solve the problem either, because now you might run into a situation where you have a lot of females that don't have a good credit history, but you have to give 30% of them a loan, whereas all the men have good credit history and you can only give 30% of them a loan. So that's not very good either. So then you can think of something like equal opportunity. Given that they are qualified, they should be equally good. But that also has problems, and it goes on and on and on and on. So it turns out that this is not so much a technical problem often, but more a political problem, or a problem that needs to be discussed with domain experts, and how you would do it without a machine learning system. So if it's that hard, if it's like MP hard, should we just give up? Is that the solution? I'm obviously advocating no, because otherwise I wouldn't be doing machine learning. But I think that we should give it a lot of thought. I think, in fact, I think at Microsoft we're looking at responsible AI as a number of different things. And these are things that we go through when we look at systems and how we create them. And making sure that they don't go bad. The first one being that the system should be fair and inclusive, so they should work similarly for everyone. As an example, with the face recognition, it should work as well for men and women, and independent of ethnicity or anything else. It should be transparent. So when you have a machine learning system, it should be apparent to everyone what data it's based on. You may not be able to tell exactly what triggered a specific decision, but at least you should know what data it's based on. Similarly to if you were talking to a human and they would make a decision based on something. And someone should be accountable. So there will be cases where it will go wrong, and in that case, someone has to be there to pick that up and to make sure you can correct the errors that are created. It should also be safe and reliable, so you don't run into these negative feedback loops or positive feedback loops. Or, for example, if you have autonomous cars, then so you don't run into a problem where it suddenly starts running into people or something like that. And of course, it should be secure and private. It should keep your data securely, but it should also not give away things about you that you don't want to give away. So we'll look at the whole process. We first look at the problem statement, and one of my colleagues has this: think of the problem and think of the news articles that it could produce. What's the worst headline because that's probably the biggest risk on this, and that's probably what we need to look at and see if we're fine with it or not, or if we're basically what we can do to fix it. So a problem like, hey, should we use your friend's recommendation to determine your credit history? Well, we already know that we created Broken Mirror episodes based on that, and that is probably not the best of ideas. But something like, should we create a model to determine if someone has cancer or not, if the cancer is benign or malign? Obviously, this is a lot of risks in terms of if we get it wrong, we might miss someone who should otherwise have gotten treatment. But on the other hand, it might also speed things up so much that we catch a lot more people that wouldn't have been caught through manual processing. So in a case like this, we would have to then look at how can we catch the fail rates. What kind of security can we put in place to make sure we're not missing someone that would have been caught by a doctor? Maybe by putting a human in the loop that reviews all the ones that were considered not to be malign. And then if we have historical data that's biased, like the CEOs, what do we do to mitigate like the feedback loops? So one way is, for example, to automatically inject some answers that keep it balanced, to keep it at the balance that it is in society, or at the balance that we want it to be. Basically avoid that feedback loop. The biggest problem, though, is probably in the selection of data, how we select data for our models. So if we look at the COVID-19 data, suddenly everyone is becoming a statistician and an epidemiologist. But here we have a problem, for example, if we compare the confirmed cases of Sweden to the confirmed cases of the United States. We have problems because these countries are very, very different. They have different populations, they have different compositions of old and young people. They have different density of people in different areas. Some areas are affected, some areas are not. But it also has a selection problem in that the people who are getting tested and confirmed are not necessarily a good representation of how many people are actually have the disease. So in Sweden, for example, we currently focus the testing on people who are either sick enough to go to the hospital and need more care, or hospital employees. And in Germany, there's a lot wider testing. So obviously they will have a lot more tested, and therefore a lot more confirmed. And they will also then have a much lower death rate, for example, than Italy, that doesn't have as wide testing. So if you compare things, make sure you compare apples and apples, and comparing two countries on these scales are very much not comparing apples and apples. The other thing is drawing conclusions from this and sort of looking at correlations. So there is a very fun site, tylerbyton.com, with a lot of like correlations that look super correlated, like 94% correlation. Basically, the curves are essentially the same. But obviously, there is no reason to think that the per capita cheese consumption has anything to do with who died becoming tangled in their bed sheets. And similarly, we see all these pictures of people who draw correlations from very, very, from just a single graph. Something like the no masks or masks, saying that these people wear masks and therefore they had these curves, and these people don't wear masks and therefore they had these curves. Or obviously, for example, China does wear masks. Now, I want to clarify, I'm not saying that masks are not useful. I'm just saying that this graph does not say anything about that correlation or not, because this is not the way to do it. In fact, there is a counter argument to wearing masks that suggests that if you wear masks, then perhaps you get like you're lulled into like false security, and you might go out even if you're sick. So either way, it doesn't matter. I'm not either on the mask or no mask, but I'm saying that this correlation is not one that you can derive from a simple graph like this. So essentially looking at confirmed as if they were the people who have the disease is not a good proxy, and that is often a problem with machine learning systems when the proxy does not correlate to the actual thing you want to measure. The model choice is also quite important. So if you have a very simple model, then you will always choose the majority. Whereas if you have a very complex model, maybe a neural network where a neural network doesn't fit, then you might learn too much about the data that you're trained on, and things don't generalize. And then you have evaluation. We have evaluation. We looked at the benchmarking, but also something like this. Let's say you're going to do a fraud detection system. You want to see if a transaction is fraudulent or not. So you have 1,000 transactions, one of them is fraudulent. You want like at least 99% accuracy. So you could simply do this. And this will obviously give you the 99% accuracy, but it will also not tell you anything about fraudulent transactions. So understanding that accuracy is often touted in a lot of these papers. Accuracy is not necessarily usually a good measurement or something you should trust. So instead, you might want to look in this case how many fraudulent got right, or even a combination of both. And then consider how the technology should be used once you created a model. So, for example, with face recognition, make sure it's not used as a perpetual lineup. And especially if you're a big company, you need to be quite responsible with things like this, and disallow these kind of uses to disallow the problem where someone is accused of being something that they are not, or that reduces privacy, etc. Or for example, like with the tie bot, if you let something loose, consider what will be the repercussions of that, what will happen, and make sure that you have a way to quickly shut it down if it goes rogue. Or we've seen a lot lately with deep fakes. We have these machine learning systems that can create fake news, and we have to now create machine learning systems that will counter that effect. Another thing that I think is good is to have a data sheet for your data set, similarly to if you have an electrical circuit that you say, okay, so this circuit is supposed to be used in these conditions, in these temperatures, and for this, but not for this. Similarly, with your data sets, talk about how they were gathered, what their problems might be, where they should be used, where they should not be used, and what their limitations are, as far as like, did you take a wide range of people, or do you know that you're missing a set of people that might need to be added on if you're going to be using this? And use diverse teams. So with diverse teams, for example, something like this would not happen. Where the Facebook name algorithm excluded anyone with a Native American name because they contained nouns and they were too long. Or, for example, creating crash test dummies that don't work for, or that don't represent half the population. So in so obviously this causes cars to be work better, or to be better tested for crashes for half the population. Evaluate for fairness, so evaluate like the different groups separately. And finally, we know that there will be errors, so find a way to deal with them. So if you have something like this, it automatically gives you a fine if you jaywalk. Things like this will happen. And this woman got fined a large number of jaywalking tickets before they figure out what happened. So put a human in the loop. And the most important thing, when you see something that's wrong, or when you feel that something is wrong, speak up, because we're not just engineers. We're the guardians of our future. Thanks.
Thanks, Tess. That was great.
Thank you.
So I was interested to see the benchmarking information, and I was surprised that there was such great improvements over such a short period of time, right? So given that things are changing so rapidly, what is something that you think is going to be changing in the next 3 to 6 months?
How do you mean something that's going to be changing? I think
Well,
one thing
everything
that I
is
would,
changing, right?
one thing that I would like to see is more and more companies doing, for example, so internally we have this group of people that actually review all the machine learning cases and figure out what could potentially go wrong with them, and making sure that we're following our guidelines, and that we're doing the best machine learning that we can do. I'm seeing some of that changing a lot, especially in larger corporations, and I'm seeing also a lot of that changing. For example, the EU is now taking on similar guidelines for machine learning in Europe, or at least guiding people. It's not a law, but it's a strong guidance to basically look through and make sure that your AI is responsible in all of those senses. So I think that's a positive.
It's interesting to see how different nations and regions are addressing different data issues. So in the future, do you see data sets? Is there value in having data sets that are a little bit more regionally specific?
Maybe if your model is supposed to be regionally specific. Yeah, definitely. The more precise you can make it, the better it will be. But also being careful that those same models are then not being used globally later, because it's quite easy to have something that's working in one area and then sort of like apply it somewhere else.
Oh, amazing. Quick question actually for you, Tess. Yeah. This might not be an easier one to answer sort of off the top of your head, so apologies. What are some of the lessons you've learned from some of your earlier projects in this space? Is there anything particular that comes to mind where you're like, oh gosh, I like personally felt this one?
I would say, so a couple of lessons is that there's often a way to do things that's not machine learning related. So there's often a way to solve a problem without using machine learning. And in many cases, I've learned that it might be preferable to do it that way unless there's a massive difference. So for example, like with the cancer detection one, you could take the images and do color decomposition and get reasonably good at it, and then you would know what you're doing. So you could sort of control your rate instead of getting a lot of unknowns. So looking at non-machine learning alternatives and evaluating them against a machine learning model. And the other thing I've learned a lot is that even in the cases where you think, oh, Fairly good. This data, like we don't need to worry about too much about it being biased. It still turns out to be biased, or it still turns out to have problems that you have to deal with later. I think are my learnings.
Yeah, no, I guess we're always learning, aren't we? Every project we do at this point.
But one thing I am a little bit worried about is we're getting into a situation, for example, with COVID-19, where we as people are giving up some of that privacy that we fought, or privacy or democracy that we fought a lot for. For example, with these people tracking apps and things like that. In order to be able to maybe go out and do other things. And so that's not necessarily machine learning related, but I find it interesting how easily we give up the rights that we're fighting for commodities sometimes. So, yeah.
So thank you for spending the time with us. And that was I really enjoyed the presentation.
Thank you.
So for our viewers, we can go ahead and if you had any questions for Tess, you can continue to add that into chat.global AI community. And thank you, Tess.
Thank you.
Hey, my name's Afunction.